Okay, last time in class, which would have been lecture number 5 on Wednesday, September 16th, we ended up with a fairly difficult problem on conservation of energy concerning the mechanical energetics of the gymnast as they dismounted the balance beam. And so I'm going to walk you through the solution to that problem and to the different steps of that problem in that video here. Remember, the key thing to keep in mind for these problems is not being able to like crank through the algebra and get the numerical answers that I show here. More important than that is recognizing in the first place that this is a mechanical energy problem, a conservation of energy problem. And you can tell that from the description of the system, and you can tell it from the things that you're asked to calculate. And so those are the kind of things that you should be keying in on these types of problems in terms of not just how they're done, but why they're done this way. Because on an exam, for example, when you see this problem or a problem like this, you're not going to see this exact problem, but something similar to this, or at least similar to parts of this. It's not going to say like, hey, this is a conservation of energy problem. Use these equations to solve it. That's the hard part. That's the biomechanics, is reading that description in English of the problem and realizing that, oh, this is something I can use conservation of energy for, to calculate these things that it's asking me to calculate. After you do that, the easy part, or at least it should be the easier part, is cranking through the algebra and plugging the numbers into the equation and solving for the numerical result. But the more difficult part ahead of that is recognizing in the first place how you solve this problem and why you solve it that way. Okay, just for review, let's go to our motivating example, which was the gymnast dismounting the balance beam here. And I'll accelerate up to the dismount here.
0.175, just the dismount.
Hasn't stuck this yet.
So the part that we are asked to calculate here is energetically what's going on from, let me see if I can freeze it at her peak height here.
15.175, just the dismount.
Hasn't stuck this yet.
Right about here at the peak height of her jump, until right about there when she slams into the mat and it brings her to a stop there. Okay, so those are the parts of the movement that we are dealing with here. Okay. So I don't have a gymnast action figure, but to visualize this, we will use Monty Mole here is going to be our gymnast, and my arm of my recliner here is going to be our balance beam, and my Kindle down here and kind of the dark leather there is going to be our mat. And so the gymnast jumps off the balance beam, they get up to some peak height here, and then they land on the mat. Okay. What's going on here in terms of energy is they jump off the balance beam, they get up to this peak height, and then they start falling down to the ground under the influence of gravity, and then they land on the mat. Energetically, what's happening there is as soon as I jump and leave the balance beam, I have a certain initial vertical velocity and also a horizontal velocity. It's a velocity vector. And as soon as I leave the balance beam there, at that instant, when I stop touching it with my body, that's when I have my greatest vertical velocity in the vertical direction. Okay? As soon as I leave the balance beam there, then gravity is the only force acting on me, and it's trying to pull me down into the ground. Okay? And so that gravity is why when Monty jumps off the balance beam here, he travels in this kind of parabolic arc-shaped path. Okay? He goes up for a little while and gets to some peak, and then goes down the rest of the way. What's happening there is he jumps off the balance beam, and gravity is accelerating him downward, accelerating him downward, accelerating him downward. When he gets to the peak height of his jump right about here, that's when he's been airborne long enough that gravity's been acting on him long enough that it's taken away all of that initial vertical velocity he had back here. Okay? So at the peak height of my jump, my vertical velocity is instantaneously zero. I still have a horizontal velocity that's non-zero, and so that's why the problem gives you a non-zero velocity initially at this peak height of the jump. It's talking about the overall velocity vector, not just the vertical velocity. But when he gets to his peak height here, his vertical velocity is instantaneously zero because he's been airborne long enough for gravity to kind of suck away all of that initial vertical velocity. Okay? Then, as he falls downward towards the mat, that's happening because gravity doesn't stop acting when your velocity gets to 0 here. It keeps acting in that negative direction and now is speeding you up in the negative direction and is accelerating you downward at a faster and faster velocity. Okay? Energetically, what's happening there is you jump and you get to your peak height here, and at the peak height, that's where you have your most potential energy. Okay? As I start falling then down to the ground under the influence of gravity, my vertical velocity is increasing. It's speeding up from 0 up here at the peak height up to some progressively faster and faster velocity as I proceed towards the ground here under the influence of acceleration due to gravity. Okay? So as I'm falling, my kinetic energy, energy of motion, is constantly increasing as I approach the ground because my velocity is getting faster. Now, where did that kinetic energy come from? Well, remember, my total mechanical energy, my kinetic energy plus my potential energy plus my strain energy, that's a conserved quantity in a mechanical system like this, when there's no like external forces other than gravity acting on Monty here that's like injecting energy into him or siphoning energy off of him. Anytime you have a system like that, his total mechanical energy is conserved. So if he's up here and has, say, 5 joules of kinetic energy, and then gets down here to the bottom and has 100 joules of kinetic energy, where did that extra 95 joules of kinetic energy come from? Well, it came from his potential energy. Up here, it was big, and then down here as he falls, it's small. Okay? So because of, in this airborne situation, because of conservation of total mechanical energy, if my kinetic energy increases by 50 joules, my potential energy has to decrease by 50 joules. So that the sum of those types of mechanical energy stays constant, so that my total mechanical energy stays constant. Okay? Then right before I hit the ground, then my mechanical energy is conserved. After I hit the ground, then some strange things happen. Then we have some other situations at play, but we'll deal with that later on in the problem here. Okay? So the initial question that we are dealing with here for the gymnast is, what is her total mechanical energy at the peak height of the jump? And then the second one here says right before she hits the mat. So like, if I go back to my example here, not after he's hit the mat, but kind of when he's falling and right before he's about to hit the mat, then what's his velocity? Okay, so those are the things it's asking us to calculate here. At the peak height, what's his total mechanical energy? And then as he's falling and right before he hits the ground, right before he slams into the mat, what's his velocity right before that happens? Okay? We can figure that out by recognizing that when I'm at the peak height of the jump versus when I'm at the lowest height right before I hit the ground, the distribution of the different types of mechanical energy is different between those situations, but the total mechanical energy in both of those situations is exactly the same. Okay? The sum of potential energy, kinetic energy, and strain energy is the same at the peak height of the jump as it is at the lowest height of the jump right before they hit the mat. Okay? Because total mechanical energy is one of those conserved quantities in physics, at least in a system like this, in a problem like this. Okay, so first problem here asks us to, or first part of the problem asks us to calculate what is her total mechanical energy at the peak height. And we're given here all of the information that we need to calculate her mechanical energy at the peak height. So let's go to Excel here, and let's write all this down. We have the mass M of the gymnast, and that's 55 kilos. We have their moment of inertia, which is their angular mass, and that was, I believe, 8.2 kilogram meters squared. Remember here, if this is a new concept for you, mass is like resistance to translation. Like the more mass Monty has here, the harder it is for me to lift him up against gravity along some path. Moment of inertia is like angular mass. The more mass he has, the harder it is for me to translate him. The more moment of inertia he has, the harder it is for me to rotate him. Or the lower his moment of inertia is, the easier it is for me to rotate him. So it's kind of like the angular analog for mass in terms of resistance to translation, resistance to rotation, moment of inertia. Okay, we also need the height above the ground that the Gymnast was. That was 1.8 meters at the peak height. We were given their linear velocity. Sorry, forgot my symbol. V. Cover up my screen here because that takes a lot of data. 0.7 meters per second. Then their angular velocity, omega, which was 4.5 radians per second. And then we also need gravity, gravitational acceleration, which is 9.81 meters per second squared. Okay, our three types of mechanical energy, remember, are kinetic energy, which there's two types of kinetic energy. There's linear kinetic energy, I'll call that LKE. There's rotational kinetic energy, RKE. There's potential energy due to gravity, which we just call potential energy. And then there's potential energy due to strain and deformation, which we just call strain energy. Okay. Notice here in the description of the problem that, at least in this first question up here, this first description for the first couple questions, we're not told anything about like material properties or stiffness or deformation. That's because when I'm airborne here, like if I'm just in the air in a jump or something like that, as far as my center of mass is concerned, there's really no appreciable strains or deformations happening at that time when I'm just under the influence of gravity here. And so that's why it doesn't tell us any information about like stiffness or deformations or anything, because we don't need to know that for this part of the problem. When we then get to the end and we slam into the mat and we deform our feet and deform the mat and deform parts of the body, then there is some appreciable strains happening and some appreciable strain energy, and we'll deal with that a little bit later on. But at least for this first part of the problem, we're not told anything that helps us calculate strain energy because we don't need strain energy yet. We're just going to assume strain energy is zero all the way through kind of the airborne part of the jump and the dismount here. Okay, so strain is going to be zero. These other three types of mechanical energy, we had fairly simple expressions for those. Linear kinetic energy was 1/2 times mass times linear velocity squared. Rotational kinetic energy was also 1/2 times angular mass, moment of inertia, times angular velocity squared. And potential energy was mass times gravity times height. Okay, so notice here the vast majority of my mechanical energy here is in the form of my potential energy when I'm at the peak height of my jump. Okay, if I take all four of these types of mechanical energy here and sum them up, that gives me my total mechanical energy, or my TME. And this is what the first part of this problem is asking for. And let me set my units here just so this looks kind of nice. We don't need any decimals here. We'll just go whole joules there. So 13 joules of linear kinetic, 83 joules of rotational kinetic, 971 joules of potential, no strain, gives me 1,068 joules of total mechanical energy there at the peak height of the jump. Okay, and that should have been the solution that I gave you for the first one here, 1,068 joules. Okay, so that is the total mechanical energy of the gymnast while they are at the peak height of the jump here. Okay, then they're going to fall through the air towards the mat here, and we're asked to calculate right before they hit the mat. So kind of at the lowest part of the jump, but before they've slammed into it, what's their velocity at that time? The way that you calculate that is by recognizing that 1,068 joules of total mechanical energy they had up here, they still have that same 1,068 joules of total mechanical energy when they get down to the bottom here. It's just that the distribution of it has changed, right? My height is now 0, so all that potential energy that I had up here, now it's 0 down here, okay? I'm also told in this second part of the problem that they've stopped rotating, they've stopped spinning, meaning that their angular velocity is now 0. Okay? So up here I had some potential energy, some linear kinetic energy, some rotational kinetic energy, and it summed up to 1,068 joules. Down here I still have that same 1068 joules, but now it's all in linear kinetic energy. Okay, the potential energy got transferred into linear kinetic energy, and the rotational kinetic energy that I had up here got transferred into linear kinetic energy, presumably by changing the pose of my body, like we talked about with the divers and with the figure skaters. Gymnasts are very good athletes at doing that as well. Okay, so that's what's happening here in this second part of the problem. It says, what is her velocity right before she hits the mat if she stopped rotating at that time? Okay, this is a great example of how you're told important things about the numbers of the problem without it explicitly telling you, hey, height is now 0 and rotational velocity is now 0. Okay, it doesn't explicitly tell you that. You have to reason that out from the description here. It says right before she hits the mat, meaning height is now 0, and it says she's stopped rotating, meaning rotational velocity is now 0. Okay? So that's why in this second part of the problem, it's crossed out not just the strain energy, which we already said we're ignoring, but it's crossed out the potential energy because her height is 0, and it's crossed out her rotational kinetic energy because omega here, her rotational velocity, is 0. Okay? So I still have that same 1068 joules of total mechanical energy, but now it's all stuffed into my kinetic energy here. Okay? Only thing I don't know in this expression here is v, velocity, so I can compute velocity there. Okay? So in this second part of the problem, the only type of energy I have is linear kinetic. And how much do I have? Well, it's equal to what my total mechanical energy was in the previous problem. Okay. Now remember that linear kinetic energy equals 1/2 times mass times velocity squared. And so now I'm going to solve for velocity. I'm going to multiply both sides of my expression here by 2 to get rid of the 1/2. I'm going to divide by mass to get v squared by itself. And then I'm going to take the square root of that to get actual v, velocity in meters per second. Okay, so that's my linear velocity, v, at bottom of the jump. And I got 6.23 meters. Sorry, 6.23 meters per second, which should hopefully be the answer that I gave you here, and it was the answer for part 2 here. Okay, part 3 is where things get a little bit more complicated. This is where we're told something about stiffness and deformation. This is asking how much does the mat deform after she hits it while bringing her to a rest if it has a stiffness of 500,000 newtons per meter. Okay? So what's happening here, let me go back to my video. What's happening here is gymnast jumps off the balance beam, gets up to their peak height, falls to the ground, and then slams into the ground, slams into the mat, and quickly, over just milliseconds, comes to a stop. Okay? It kind of looks there like we're violating conservation of energy, right? I get to my peak height, where I've got very little kinetic energy. I then fall to the bottom, where all my potential energy has now become kinetic energy, and I'm moving at this fast velocity. Okay? I then slam into the ground, and I stop moving. All that kinetic energy goes away. Okay? So it looks like I violated conservation of energy. Well, no, I didn't really. All I'm doing here is I'm expanding my system. My system has expanded from just the gymnast to now it's the gymnast plus the mat. Okay? So where did all that kinetic energy that the gymnast had before they hit the mat, where did it go? It went into the mat. She deformed the mat and transferred that kinetic energy that she had, energy of motion of her center of mass, into the mat in terms of the strain energy stored in the mat. There's also a little bit of it stored in like the deformations of the gymnast, like the deformations of the surfaces of her feet and the cartilage in her joints and things like that. But that's pretty small compared to the much larger deformations of the mat. So here we're going to assume that it all went into the mat. So this is pretty similar actually to the second problem, where we still have this same total mechanical energy. It's still 1068 joules. My strain energy plus my potential energy plus my kinetic energy is still going to be a total of 1,068 joules, or my TME is still KE plus PE plus SE. Okay? The difference here is now I've hit the mat. Okay, now I'm standing on the mat, now I've deformed the mat has brought me to a rest. So I'm at rest, meaning my potential energy is 0. And I'm on the ground, meaning my height is 0, my potential, sorry, I said that backwards. Let me start up here. I'm at rest, meaning my kinetic energy is 0. I'm on the ground, meaning my height is 0, my potential energy is 0. So all of that 1,068 joules of total mechanical energy that I have in my system here, now it's all in strain energy. Okay, and my strain energy, that's equal to 1/2 times K, which is the stiffness of the mat, times x squared, which is the deformation of the mat. Okay. So let's add my stiffness here. K, that was 500,000 newtons per meter. What this means is you'd have to apply a force of 500,000 newtons to the mat to deform it by 1 meter. It's a pretty common expression for how stiff a material is. So we're asked to solve for how much does the mat deform when she lands on it, which is basically asking us to solve for x, solve for the deformation of the mat. And we can do that by recognizing that the left-hand side of this equation is equal to 1,068, and k is equal to the 500,000 that we were given. And now we just need to solve for x. So I'm going to multiply by 2 to get the 1/2 out of the way. I'm going to divide by k, my stiffness, and then I'm going to take the square root because it's x squared in that equation. And I get 0.065, which is the answer that I gave you here. Hopefully it is. 0.065, right? So 0.065 meters, which equates to about 6.5 centimeters of deformation of the mat, which is, I don't know, maybe about that far or so. Seems like kind of a lot, but gymnastics mats are pretty squishy and pretty thick, and they deform quite a bit to give you a nice soft landing for kind of these high impact landings that these athletes do. Okay, the last part here, last question that it asks, is a simple calculation, but conceptually might be the hardest part of this problem. It says, what is the average vertical GRF applied to the mat, or also you could also think of this as being applied to the gymnast while it's bringing her to rest there, while it's taking away her kinetic energy and storing it as strain energy in the mat. So what's the average vertical force applied to her while that's happening? The concept there is that, remember, in order for the total mechanical energy of a system, like the gymnast here, to change, in order for it to go from 1,068 before she hit the mat to 0 after she hit the mat, something has to do work on them to take that energy away or to change their total mechanical energy. So that's what's happening here when the gymnast falls and slams into the mat here. Okay, the mat hits them, or they hit the mat, and they develop a force between them and the mat, a contact force or a ground reaction force. And that ground reaction force is doing work on the gymnast as a system to take away their mechanical energy and transfer it into the mat. Okay, so the gymnast's total energy here went from 1,068 before they hit the mat to 0 after they hit the mat. How did that get accomplished? Well, the mat did work on them to take that energy away. And how much work did it do? Well, if the gymnast lost 1,068 joules of energy by hitting the mat, then the mat had to do an equal amount of work on them, 1,068 joules of work, to take that energy away. Okay. So, since the gymnast lost 1,068 joules of mechanical energy, the mat gains 1,068 joules of mechanical energy, meaning the work done by the mat on the gymnast equals that change in energy, that 1,068 joules. Okay. Work, W, is equal to force, or average force, times displacement, or distance traveled, which in this case is our deformation, our x that we just previously calculated, that deflection of the mat here. You could also think of this as how much the gymnast sunk into the mat while it was bringing her to a stop. Okay? So I've got my work, W, I've got my X, my displacement, and so I just divide work by X to get the force there by itself. So the average force applied to the gymnast while they were being brought to a stop here was about 16,000 newtons. Is that a lot? Let's scale it by their body weight here. So let's divide 16,337 newtons by mass times gravity. And we get that the average force applied to the gymnast while they're landing here is about 30 times their body weight. That's a really big force to be applied to an individual. If you're running, for example, every step that you take when you're running, the peak force that you apply in terms of your vertical ground reaction force is maybe 2, maybe 3. Maybe if you're running real fast, maybe up to like 3.5 times your body weight here. Okay, so this force that they're experiencing is roughly 10 times the peak force that you develop when you're running. But there's some caveats here. There's some special considerations there that make this not really an injurious force a lot of the time. Gymnasts get a lot of injuries, and a lot of them come from landings and impacts like this. But there's some special cases or some special considerations here why it doesn't like more frequently cause injuries. One, they're landing on both legs, and so the force, if they're landing kind of symmetrically, the force under each leg is only about 15 times the body weight here, whereas in running it's all on that one leg. So it's not really 10 times the load in running. It's really more like 5 times the load in running. So it's still a lot, but it's not quite as bad as if it was one leg. Also, the load there is applied for a really short amount of time. Okay, they come to a stop really, really fast, like milliseconds, and from after they hit the mat. And so yeah, it's a really big force, but it's a fairly small impulse in the sense that real big force is not applied for a very long amount of time. Okay, and that's one of our means for using mechanics to protect from injury in impacts like this. If you can spread it out over like a shorter period of time, then the impulse isn't very big, even if the force is pretty big. Kind of gets at to like what's causing the injury. Is it the force? Is it the impulse? Is it the work? That's a difficult question. We don't really know. It kind of depends on a case-by-case basis. But one way that you can keep the impulse low, if we think impulse might be the problem, is by just simply not applying that force for a very long amount of time. Okay, that is it for this one. Again, please try and work through that problem, and hopefully if you're struggling with it, this video will help you. Also notice, if you didn't see the announcement I just posted earlier today on the course website, I posted another like fully worked example of doing this type of problem involving like a martial arts maneuver, which is kind of a similar, at least conceptually similar situation. So please take a look at that one as well. There will be a problems like this on the exam. Not one that's like this long and involved as like a single problem, but kind of different smaller problems that capture these things here. Okay, good luck.